Hi everyone. In this section we will talk about the wave interactions, how wave interact with one another. So first title which we are going to study is interference. Interference is about the waves which can meet each other and interact with one another. Interference means a meeting. If two objects meet each other, so it's called interference. First, we are going to define the difference between the material objects and the waves. So with this sentence, we are going to start. Two or more material objects cannot occupy the same space, but two or more waves can. So these two bumper boats cannot occupy the same space because they are material objects. They cannot stay at the same volume, at the same space. They can stay side by side. But waves are not like this. While there is an orchestra playing different instruments, a person can hear the sound of different instruments at the concert at the same time. So maybe you can say that for bumper boats. So first you are going to occupy the space, then blue boat will occupy, then red boat will occupy the space. But you cannot say the same thing for the waves. They can occupy the same space at the same time. This means that many waves can occupy the same space at the same time. That's why you can hear the sound of every single instrument at an instant at the same time when an orchestra is playing music. As two or more waves pass through each other, they interact with one another. This interaction is called interference. So interaction between the two or more waves as they pass through each other, this interaction is called interference. As two or more waves overlap, a resultant waveform is produced for an instant. So let's show it by a simulation. I'm going to now produce some waves on this animation. First I will send a pulse and it will reflect. After it reflects, I am going to send one more pulse. And when they meet each other, you see that they're interacting with one another as they pass through each other. So that interaction is called interference. Two waves, as they pass through each other, they interacts. This interaction is called interference. So as two or more waves overlap when they pass through each other, a resultant waveform is produced for an instant. So two waves, if two waves are interacting, so for an instant, these two waves interact, and then you are going to see, instead of these two waves, a single waveform. So this resultant waveform is the combination of two or more overlapping waves. So that resultant waveform, so it's a single wave is due to the combination of two or more waves which are overlapping. This method of combining two or more overlapping waves is called superposition. So we are going to add them and we are going to draw the shape of that resultant waveform. So that method for adding two waves is called superposition. Superposition, in fact, in mathematics is meaning of adding, especially adding the vectors are generally represented by superpositions. Superposition principle is explained in the book as when two or more waves meet in the same medium, the displacement of the particles of the medium is the resultant, which is the vector sum of the individual displacements. So, for example, here you see two waves. Wave 1 is above, wave 2 is below. They are in the same medium, in fact, but I separated them. When they at the same medium, they overlap. So resultant wave is going to be vector addition of the individual points. For example, if I draw a line in here, so this point's interaction displacement is in positive y direction. Say that it is 2 centimeters. This point displacement is again in positive y direction. Say that it's 2 centimeters because they are equal. It seems to be equal. So resultant wave will have a displacement which is equal to 2 plus 2, which is equal to 4 centimeters. This is what superposition principle does. So if the displacement directions are in the same direction, you are going to add them. For example, let's choose another point. I'm going to choose here as a point. So there now the first wave is causing the particle to vibrate in negative y direction. So it's 2 centimeter negative y. Second one is almost identical, 2 centimeter negative y. So resultant wave will have 2 plus 2, which is equal to 4 centimeters negative y directions. So this is an example how we can combine two waves, and then we can draw the resultant wave. That resultant wave will appear as these two waves, wave 1 and wave 2, interfere in the same medium. This is what superposition principle is. So when two or more waves meet in the same medium, displacement of the particles of the medium, if you want to find the displacement of that point, it's going to be the resultant vector sum of individual displacements. So you are going to add the displacement due to the first wave, you are going to add the displacement due to the second wave, you are going to find what the resultant displacement is. So there are two types of interference. One of them is the constructive interference. If the particles of the medium are vibrating in the same direction, so this is called, these waves will support each other, and then, so as you see, wave 1, this is the first wave, and wave 2, which is the second wave, so they are moving in opposite directions. Of course, they must move in opposite directions to meet, otherwise they cannot meet, so they must move in opposite directions. So if their displacements are in the same direction, so as you see, both are in positive y direction, this is positive y direction, that's also positive y direction, so when they meet, they are going to form a constructive interference. Now in this simulation, you are going to see two waves moving in opposite directions in the same medium, but I separated them. First wave will appear on the rope above, second wave will appear on the rope below, and the resultant will appear on the third rope, which is in the bottom. So now let's send two waves. Okay, so they're approaching each other, and then let's stop it a little more. Okay, so in fact, as I said, this is the wave 1 and wave 2, both are moving in the same direction. First wave has a amplitude, or this point has a displacement or amplitude which is equal to 2 centimeter above. Second wave has a 0.5 centimeter above. So resultant is going to be sum of them, which is going to be 2 plus 0.5, which is going to be 2.5 centimeters, as you see. This is what constructive interference is. So you are going to add the amplitude of each wave, so you are going to find the amplitude of the resultant pulse. In constructive interference, so the resultant wave's amplitude is going to be the sum of the amplitude of each pulse, and of course, when you add them, resultant amplitude will have a greater than the amplitude of the individual waves. This is the amplitude of the first wave, this is the second wave. So as you see, first wave's amplitude, second wave's amplitude, but resultant wave's amplitude will be much greater than, because you are going to add these two amplitudes, so you'll find the resultant wave's amplitude. Assume that first wave has an amplitude of 2 centimeters. Let's give some numbers. 2 centimeters. Second wave has an amplitude, say that 4 centimeters. Resultant wave will have an amplitude which is equal to 2 plus 4, 6 centimeters. So this is how constructive interference occurs. What if the particles are vibrating in opposite directions? In this case, they will weaken each other. So it's called destructive interference. So if the displacement of the vibrating particles in opposite directions, just like this, one particle is vibrating in positive y direction, one wave is vibrating in positive y direction, other wave is vibrating in negative y direction. So in this case, they are going to destructively interfere. They will weaken each other. Let's see this animation. Now let's see the simulation. So two waves are approaching each other in opposite direction. They are vibrating. So at this position, let's stop it. So as you see, each wave is in opposite direction. One wave is vibrating in positive y direction with 2 centimeters. Other wave is vibrating in negative y direction with 2 centimeters. So they will cancel each other. As you see, resultant amplitude is going to be 0. Or if you choose another point, so this wave is vibrating in positive y direction with 2 centimeters. The other way is almost 0. 2 minus 0, it's going to be resulting is going to be 2 centimeters in positive y direction. So you are going to subtract the displacement of the displacements because they are in opposite direction to calculate the resultant of the vibrating point on the resultant wave. So if the waves are vibrating opposite directions, just like this first wave and second wave, resultant will be the difference between the pulses. So the amplitude of the resultant wave is the difference between the pulses. You are going to subtract them. Let's give numbers. For example, for the first wave, say that first wave has an amplitude of 4 centimeters. Second wave has an amplitude of, say that second wave is an amplitude of 3 centimeters. In this case, resultant is going to be 4 minus 3, 1 centimeter, and its direction will be in the same direction of the wave, which is greater in amplitude. And also, you are going to see that this resultant wave's amplitude will be less than the displacement of the wave that has a greater amplitude. So greater amplitude wave has 4 centimeter displacement, but resultant is 1 centimeter. It's going to be always less than the amplitude of the greater component wave. So this is what destructive interference is. But when two waves meet each other and interfere, and after that they pass through each other without any change, they keep their original shape and travel in the same direction. So this is the wave 1 before interaction. This is wave 2 before interaction. This is when they interfere. But after interaction, second wave goes on its own wave. So it was moving in positive x direction, again moving in positive x direction. And also its amplitude will be the same, shape will be the same, so you cannot change their shape by interference. There is nothing happens to the waves as they interfere when they interfere with one another. Or this first wave this is the second wave, they are destructively interfere at this point, but then second wave goes on its way with the original shape, original amplitude, original speed. There is nothing changes. First wave goes on its way without any change. But if the waves have equal amplitudes, but they vibrate in opposite directions, if they coincide, if they overlap, just like this one, first wave, second wave, because they are equal in magnitude and opposite in direction, their amplitudes, they will completely destroy each other. So the two waves completely cancel each other as if there were no disturbance. For an instant, you are going to see the shape of the rope is going to be as if there is no disturbance. This situation is known as the complete destructive interference. So amplitudes must be equal, but all direction of displacement must be opposite. In this case, two waves destroy each other, which is known as complete destructive interference. And superposition principle holds true for both mechanical and electromagnetic waves. So light also interfere, or all of the other electromagnetic waves can also interfere. In chapter 7, we are going to talk about this interference. And also these transverse waves, these examples, all these examples were about the transverse waves. Longitudinal waves can also interfere. Superposition principle is valid for longitudinal waves as well. So, but a bit different. Remember, in longitudinal wave, compression corresponds to a point with a region of a higher pressure, and rarefaction or stretch region corresponds a point of or region of lower pressure. So when two waves move in opposite direction to longitudinal waves, if they interfere constructively and destructively, it's going to be like this. For example, right now, one wave's compression and other wave's compression meet each other, so you are going to, resultant is going to be much more compressed region. Another compression meets another compression of the second wave, again you are going to see a much more compressed region. So as you see, pressure also increasing for the resultant wave. If compression and compression meets each other, so they are going to the compression or stretch region meets to a stretch region, so much more stretch region. So it's going to be the constructive interference. Compression meets compression, or stretch region, which is called rarefaction, or stretch region, another rarefaction, interfere. So it's going to be constructive interference. But if one compression and one rarefaction meets, now I'm going to try to stop the animation so you are going to see what happens. So when they meet each other, okay, right now, look at here. So one stretch region and one compression means, as you see, you are going to see a region, almost there is no disturbance. So destructive interference, and compression and rarefaction. When they interfere, compression of the one wave interfered with the rarefaction of the another wave, so result is going to be zero. As you see, there is, it seems to be medium, almost have no disturbance. Okay, a sectional question. A wave of amplitude 0.30 meter interferes with a second wave of amplitude 0.20 meter. What is the largest resultant displacement that may occur? Largest resultant displacement occurs at constructive interference. Constructive interference. So we are going to draw two waves. One of them is 0.30, the other one is 0.20. They are approaching each other. So this is amplitude is 0.30, other's amplitude is 0.20. When they meet each other, of course, they are going to support each other, and then resultant amplitude is going to be y1 plus y2, which is 0.30 plus 0.20, which is going to be 0.50 centimeters. And another interaction of the waves with its environment is the reflection. Waves can reflect back from a point in a medium. Before starting in reflection of the waves, first I'm going to explain something which is additional about the waves. As a wave is moving just one in here to the right, so I am going to draw two different positions of the wave. Initially, wave is at this position. Final position is the position indicated with this red pulse. You are going to observe that this point is vibrating upward. So every point in front of the wave will vibrate away from the equilibrium position. And every point behind the wave will, at the back of the wave, will vibrate towards the equilibrium position. So this will help you to understand how reflection occurs, this information. So as a pulse travels to the right, the points in front of the wave vibrate up away from the equilibrium position. The points at the back of the pulse will vibrate down towards the equilibrium position. Two types of reflection we are going to study. One of them is the reflection at the fixed boundary, the other one is reflection at the free boundary. Fixed boundary, so assume that there is a rope. Rope is attached to the wall very tightly, so this is the fixed boundary. But if you make this rope free to vibrate, I mean by making a hoop or a ring, so this is going to be a free boundary. So we are going to send two pulses on this rope, so towards this fixed and free boundary. First, let's study the one at the fixed boundary. Now, by animation, let's see that what happens. In fact, as it's moving by using this YouTube video, I'm going to show it to you. First one is
to demonstrate the reflection and transmission of waves on springs. Firstly,
okay. First, let's see that. Oh, right now, a wave is now transverse wave is approaching on the right of the equilibrium position. After reflection, it will turn to the left, as you see. So from fixed boundary, an object, a wave is traveling to a fixed boundary, will be reflected, and also it will change direction of the vibration. So let's see another wave, ascend. So as you see, as soon as it arrives the fixed boundary, it reflects by changing its direction of vibration. So this is about how a wave reflects from a fixed boundary. But if the end is free to move, free to vibrate, just like a ring, so you see that direction of the vibration will not change. So it's going on the right and also reflecting from the right. So this is the reflection from the free boundary. Only it reflects, but there is no change in direction of the vibration. So what is the reason for that? Now we are going to try to understand this. When a pulse reaches to the wall, when this pulse reaches the wall, so because we know that every point in front of the pulse vibrates upward, of course when this pulse reaches the wall, it will apply a force upward direction on the wall. So drop exerts an upward force on the wall because the particles are vibrating upward away from the equilibrium position for a wave which is moving to the right. But we know that if this is the action force on the wall, every action is a reaction. So this wall will apply a reaction force on the rope. Direction of the reaction force is on the opposite direction. The wall in turn exerts an equal and opposite reaction force on the rope. So that reaction force causes this pulse to be inverted. So this downward force, this reaction force on the rope causes a displacement in a direction opposite to displacement of the original pulse. So as a result, this pulse is inverted after reflection. So it reflects and also it inverts, reflects and inverts. And after that, this pulse will continue its wave by changing its direction of vibration. But if the end is free, it's not going to be like this because there is no action reaction force on the rope. So because the end is free to vibrate, when the pulse reaches the boundary, the rope is free and free to move, and it pulls the ring up with it and then down again. So it will move up, down. There is no action reaction forces between the rope and the post. So then the ring falls back down to its previous level. The movement of the rope at the post is similar to the movement of that would result if somebody were to whip the rope up and send a pulse to the left. So that's why this pulse will only reflect, but there will be no change in direction of the vibration. So then we can say that if a pulse is sent to a free boundary, so it will only reflect, there will be no change in direction of the vibration, not inverted. It's going to be like that. Okay, a sectional question. A string is rigidly attached to a post at one end. Rigidly attached means fixed. It's going to be a fixed boundary. Several pulses of amplitude 0.15 meters sent down the string. So first pulse, second pulse, third pulse. So many pulses are sent. Sent down is a phrasal verb by the time. It doesn't mean that sent from down. Sent down is phrasal verb. And they reflected at the post. They will reflect and travel back down. Travel back down also phrasal verb. It doesn't mean that it's from down. The string without a loss of amplitude, so amplitude of the incident wave and the reflected wave will have the same number. What is the amplitude at a point on the string where the maximum displacement points of the pulse crosses? Maximum displacement point, what does it mean? It's the crest, representing the crest of a wave or the trough of a wave. So the question is asking when the crest and the trough meet, so what's going to happen? So we know that this end is the fixed end, so because it's fixed end, this green pulse will be inverted and reflected. As you see, it's inverted and also reflected. Of course, sometime later they will, this purple one and then the green one will meet. Because their maximum displacement points meet, which means crest and trough meets each other. So because their lengths are the same, amplitudes are the same, 0.15 meter up, 0.15 meter down, so they will completely cancel each other. So you are going to see a complete destructive interference and amplitude becomes 0. So what is the amplitude at the point on the string when the maximum displacement point of the two pulses crosses, so it becomes 0? What type of interference is this? It's a complete destructive interference. What if the end is free? If the end is free, this green wave will reflect first, and there will be no change in direction of vibration. So when they meet each other, of course, this time they are going to support each other. So 0.15 is the amplitude of the one wave, 0.15 is the amplitude of the other wave. So resultant amplitude is going to be 0.30, and it's a constructive interference. Okay, this is all about the interaction, but we have one more title we are going to study in the next lesson, standing waves. See you next lesson.